In this video, we will see how we can combine the problem-solving principles of kinematics with Newton's second law. The problem begins in a very bizarre and unfortunate set of circumstances. An elephant with a mass of 1,150 kilograms and a cockroach with a mass of 2.52 grams are both falling off of a cliff that is 37.3 meters high. We will neglect air resistance, so both animals can be considered to be in free fall. And we are first asked, how long does it take the animals to reach the ground, and how fast are they traveling when they hit the ground? Well, this starts off as a standard kinematics free fall type of problem, so we will follow the usual procedure for such problems. Step one is to figure out what the problem is trying to tell you. As with all kinematics problems, we have 6 variables that we consider: the initial position, the final position, the initial velocity, the final velocity, the acceleration, and the time. Now we can make this statement for both of the creatures, that their initial position is the top of the cliff, which is 37.3 meters. Their final position will be the bottom of the cliff, which we shall call 0. Their initial velocities will both be 0 because we state that they fall off the cliff, not that they jump or are thrown, but they simply fall off the cliff, so they begin with a velocity of 0. And then finally, we know that they are in free fall, and so they will have an acceleration of 9.8 meters per second squared. Notice we put the negative sign to signify that that acceleration is downward. Step 2 in the process is to figure out what the problem is asking you for. And looking at the problem statement, we see that we're actually asked for both of these. We are asked for the time it takes for them to reach the ground and their velocity just before they hit the ground. Right? So the entire data table will eventually be covered. But the first question that we are asked is, how long does it take the two animals to reach the ground? Now note, they will reach the ground at the same time because we are neglecting air resistance, and in the absence of air resistance, a free-falling object has the same acceleration regardless of its mass. Let's call this acceleration 9.80 so that we can retain 3 significant figures for this exercise. So they will both have the same free fall acceleration regardless of their mass, so they will both hit the ground at the same time. To discover what that time is, we look at step 3 in our problem-solving process, which is to consider what is irrelevant to the problem to guide us to the proper equation. For this first question, how long does it take them to reach the ground, the final velocity is irrelevant. We are initially not given it. We are initially not asked for it. So we find the equation that does not involve the final velocity, which would be this equation right here. Final position equals the initial position plus the initial velocity multiplied by the time plus 1/2 times acceleration times time squared. The final position is going to be 0, and the initial velocity is 0. So we see that the equation has become simplified with 0 final position. The initial position is 37.3, and the acceleration is negative 9.8. That negative sign is very important. We bring this over to the other side, it becomes positive, and we have 4.9 times t squared equals 37.3. Solving for t, this gives us a time to fall of 2.76 seconds. That is the time it will take both animals to fall. We then address the second question: what is their final velocity just before hitting the ground? There are a couple of different ways that this can be accomplished. The most straightforward way is to say that the final velocity is the initial velocity plus the acceleration multiplied by the time, with the initial velocity being 0. We say that the final velocity is then negative 9.80 multiplied by the time to fall, 2.76. And that gives a final velocity of negative 27.0 meters per second. Now, the risk here is that if we miscalculated this time, then that error would carry over into this calculation. We could use the last kinematics equation to find that final velocity as well. You can do that as an independent exercise and confirm that you get this final velocity. So that solves the first part of the problem. We then see that the soft ground brings the animals to a stop in 0.0125 seconds, a very, very sudden stop. We were asked to calculate what is the acceleration that brings them to a stop, and then use Newton's second law to calculate the net force that they feel. And use that net force to explain why the elephant will likely be killed by this fall, but the bug might be able to walk away. So now we have a second situation. This first situation was falling, but now we deal with the situation of coming to a stop. And we'll have these 6 variables, once again: initial position, final position, initial velocity, final velocity, acceleration, and time for this situation of coming to a stop. Once again, we look at our problem-solving procedure and we say, all right, what do we know coming into the problem? Well, we know that just before they hit the ground, they have a velocity of negative 27.0 meters per second. Again, the negative sign meaning they're traveling downward. When they are finished coming to a stop, they will have a velocity of 0. And this takes 0.0125 seconds to occur. Those are the things that we know. We are asked for the acceleration in this case by the first question, and we do not know either the initial or the final position. Presumably the final position is the ground, but we don't know how much the ground dents when they hit the ground. So finding the acceleration in this case is just a simple matter of using the definition of acceleration itself. V final minus V initial divided by the time. The final velocity is 0, the initial velocity is negative 27.0, and the time is 0.0125. This gives us a very high acceleration of 2,160 meters per second squared. Notice that the number is positive, indicating that the acceleration is upward, an upward acceleration to bring their downward velocity to a stop. This is the acceleration of both the elephant and the cockroach. There is no difference between the acceleration of the two. They have the same starting velocity, the same ending velocity, and come to a stop in the same period of time. The difference will occur when we go about calculating the net force felt by the elephant and the net force felt by the bug. We calculate that net force using Newton's second law. Net force equals mass times acceleration. In this case, we know that the mass of the elephant is 1,150 kilograms. That didn't matter earlier in the problem, but now that we're worrying about net force, it matters now. And the acceleration is 2,160 meters per second squared, as we calculated up here. That gives us a net force felt by the elephant of 2,480,000 newtons. That is the net force required to bring the elephant to a stop. We do a similar calculation for the bug, the difference being the bug has a much smaller mass, 0.00252 kilograms. Notice we must express the bug's mass in kilograms, not in grams, to get the net force. So the mass of the bug is 2.52 grams. Well, we convert that to kilograms with our unit conversion method, putting grams on the bottom so grams cancel, and realizing there are 1,000 grams in 1 kilogram. So that gives us a mass for the bug of 0.00252 kilograms. And that's a net force of 5.40 newtons. Looking at these forces, we can see why the elephant is in so much danger. A newton is not a very large amount of force, but 2,480,000 newtons is a deadly amount of force. The elephant has a very high mass, and so it has a large amount of inertia. This means it's very difficult for the ground to bring the elephant to a stop. It must exert a huge amount of force to bring the elephant to a stop, enough probably to kill the elephant. Whereas the insect has such a small mass, the ground does not have to exert so much force to bring the bug to a stop, and so 5.4 newtons is a small amount of force, and the bug might be able to walk away.